So, with regards to Matmerize, then, do you have any, or can you share any maybe like case studies or maybe hypothetical examples of like who your customers are and the specific value that you can provide to them with these data sets and algorithms, etc.
Yeah, so we're lucky to be engaged with customers in a variety of different spaces. I mean, that's one of the exciting things about working at Memrise is that you get to work on different sectors, whereas in research, like you said, I just graduated. We do work on different problems, but it's still just a handful. So yeah, at Memrise, we're engaged with people in several spaces, including
Hello, everyone. Welcome back to the It's a Material World podcast. I'm your host, Puneeth, and joining me is my co-host, David. David, how's everything going in California at Tesla, etc.?
Pretty good. Yeah, recently been doing some more data science work, doing some SPC, statistical process control, and some CPK, which is like basically just one number to tell you how define your processes. So really as a process engineer trying to get a better idea of how our process goes from day to day and get things more under control. So utilizing a lot of data science skills I've learned along the way recently. So it's been different and refreshing, I guess, to do some different stuff. So yeah. How about you?
Yeah, things are going well. You're talking about like CPK, PPK, and things like that, and I was like, okay, like cool. Like we do a little bit of the same thing from the statistical side of things, and I think there is that integration between process engineering, quality engineering, design, etc. But I think that actually carries over well to the topic of today's episode, which is just essentially AI and machine learning and being able to predict properties of new polymers. And we bring on Dr. Rishi Gurnani from Matmerize to really share his insights into AI-enabled discovery of new polymers materials. So I thought it was a really fascinating conversation. I learned a lot, and I think it would be especially important for current students or early career professionals because I really do think, and you can listen to, any previous guest and they'll say the same thing. We've had a lot of advice on this, but it seems like AI and ML will just continue to make a bigger and bigger impact in this space of material science and engineering. So I just wanted to see if you had any highlights from the episode that you wanted to emphasize, you want listeners to look out for.
Yeah, I think that Rishi really gives a good overview of how their model works. And so for those more inclined, it's very interesting to hear more of the specifics. Especially, I think the most interesting part is how they take language-based text and give it some sort of meaning in the physical world. For example, he was talking about polyethylene. And so it's very common in a lot of these different fields where you have to give like basically either statuses or names, like numerical value, so that it's easier for the model to crunch the number and predict by giving out another value. So I thought that was very interesting because he was talking about how they basically tokenize a name into numbers that have physical meanings so their models are more accurate and it can be easier to realize what is most important in a material system. So I thought that was extremely unique and something very interesting that they do. And it's just like a very common and very good data science technique to do this. So I thought overall it was fascinating to hear about how they can hone down and create these models for such complex systems.
For sure. I think what was particularly interesting to me was the application of those models and the impact that it can make for their customers. So we dive into a couple case studies, one with Kimberly Clark, and without going into too much detail, the impact was like particularly astounding for me of just the way that they can help accelerate the research and development cycle to distill, thousands of options into a select few that a Kimberly Clark, R&D engineers and scientists can then run with and get a better idea, and that can help accelerate their cycle to get that kind of next improved product. So there's a lot to discuss here, and Rishi also like makes sure to share really actionable and specific advice on how he got how he learned coding, even though he's not like a computer science or computer science major. He got his bachelor's in MSE, and then his PhD was also in MSE. So be sure to be on the lookout for his advice on how to gain that experience. I know, David, you've done some similar things as well. So I think it's really worked for you. It's worked for him. It's worked for him. So we have a lot to discuss here. And so without further ado, let's get into it. Hello, everyone. So for today's guest, I'm happy to welcome Dr. Rishi Gurnani, a very recent graduate from Georgia Tech's MSE PhD program. Rishi's PhD work focused on AI-enabled discovery of new polymer materials using publicly available data, specifically looking for polymers that enable energy storage and gas separations. Rishi also holds a bachelor's in MSE from UC Berkeley. He has had internships at Tesla and General Motors, working on adhesives and paints, and his current role at Matmerize, where he's actually been working for several years now, leverages his expertise in AI to develop new polymer discovery methods. Rishi, thanks so much for coming on the show today.
Thank you so much for having me. It's a pleasure to be here.
Yeah, let's just go ahead and get started. First, we want to know how AI can be used in polymer discovery. We want to understand at a deeper level what kind of algorithms are actually being run to generate these AIs, and then maybe dive into what data you have to feed in and what data you get out for these applications.
Sure. So I think we should start with maybe the challenges of polymer discovery. And one of the challenges is that the space is massive. And by polymer universe, I mean the space of all polymeric materials that could be made if only we had enough time. For example, the number of polymers that could be made by functionalizing polystyrene alone is over 10 to the 14th power. And so this space grows as you go beyond polystyrene. And so out of all these possibilities, the optimal polymer changes depending on the application of interest, whether it be packaging or something more high tech like electrically insulating films. So, artificial intelligence then can accelerate our convergence to these interesting cases among the vast polymer universe due to AI's ability to basically crunch numbers at a scale that's challenging even for humans. So, turning this vision of AI assisted materials discovery into a reality didn't happen overnight. One of the key players in this space is Dr. Rampi Ramprasad, who's my PhD advisor and also the CEO of Matmerize. He's been putting kind of the critical pieces together for over a decade now. And these key pieces include, of course, the creation of data sets, investment in computational resources, and also AI algorithms tailor made for chemistry, physics, and material science. These technologies have been developed within the Ramprasad group at Georgia Tech and have since been exclusively licensed by Matmerize a couple of years ago. Since licensing those technologies, we've built on these and have developed our own in-house IP. So that's polymer discovery kind of at a high level, and also a little intro, I guess, into how Matmerize was founded.
Cool. So with regards to Matmerize then, do you have any, or can you share any maybe like case studies or maybe hypothetical examples of like who your customers are and the specific value that you can provide to them with these data sets and algorithms, et cetera?
Yeah, so we're lucky to be engaged with customers in a variety of different spaces. I mean, that's one of the exciting things about working at Memrise is that you get to work on different sectors, whereas in research, like you said, I just graduated, we do work on different problems, but it's still just a handful. So yeah, at Memrise, we're engaged with people in several spaces, including consumer products, pharma, semiconductors, plastics and packaging. And we've also had a lot of traction around sustainable materials. In terms of how we help them, there are some specific case studies that, maybe we can get into later on, but I'll keep it high level for now, which is that users can use their own data to train custom models on our platform. Or if they don't have data, they can benefit from models that we've developed that are stocked on the platform from day one of their subscription. So with these models, they can predict things like electronic properties, mechanical properties, thermal properties, gas permeabilities, and more. I mean, there's dozens of properties. So that's one component is the model training, whether you're doing it using your data or our data. And then, there's the prediction component, the screening component. So then you can create a big space of cases that you're interested in testing, screen them virtually, and then narrow down on a handful that you actually want to go and explore further in the lab. And we have tools built around that to help you build the space, to help you analyze the results, whether it's from the model training or from the predictions, or maybe you want to figure out, does my data set look good? Is it ready for training? We have a feature that will tell you, that will basically bring up warnings or errors that we've identified in your data set. So that's kind of the high level of what Matmerize provides its users.
Awesome. Yeah, maybe to dive just a little bit deeper, what type of data do you feed into the models? And then maybe more specifically for your customers, is it as easy as saying like these are the ideal properties I want, and then the model is adept enough to be able to take those inputs and do like a basic global optimization to find those? Or maybe in that way, could you describe it in a bit more detail how it's functionally used?
Yeah. So in terms of like AI algorithms, my work and kind of the work of the team falls into two main areas. One area is structured property modeling, and then the second is structure generation algorithms. So in the first case, structured property models, we're building a model that can answer the following question. Given a chemical structure, say that of a known polymer like Kevlar, what is a reasonable estimate of its various properties, such as glass transition temperature or TG, band gap, dielectric constant, etc. The model can answer these questions not only for known polymers, but also for polymers that have never been made before. And that's the real power. So, say polymers like Kevlar with methyl groups attached, or structures that are even more exotic than that. And in these cases, the data sets are basically, at its most simple level, are of the form of structure and property. So you have a bunch of different rows, and then you have listed the structure and then a property. And depending on how complex the property is, chemistry may not be enough to describe that property. So you may also include molecular weight, temperature, maybe there's additives that are in there as well. And so all these additional degrees of freedom can be added in. So that's the structured property modeling piece. But the other piece, structure generation. So, how do we actually create these exotic structures that we want to screen? I mean, we could use our brain, but as I mentioned, the polymer universe is massive. So if we actually wanted to list out every polymer that's in there, we'd need to set aside a huge chunk of time to write all of those down, probably more than our lifetime. So the other option is you could use an algorithm to do so. But if you do, then you need to take some measures to make sure that it's not just throwing out crazy pie in the sky structures. You want to make things that can actually be synthesized. And so that's the type of question that we're trying to answer with our structure generation algorithms. How can we sufficiently explore the space, but also constrain it so that it's meaningful for the chemists who would actually take in these recommendations?
Awesome. And yeah, well, I think we'll get into a case study or specific companies potentially later on in the episode. But for now, I want to dive into, you have this background where you have your PhD, but then you also have your work with Matmerize, and it sounds like they're integrated, or your PhD work funneled well into your work at Matmerize. So can you just describe the differences in the environments between these areas of industry versus academia, like work expectations, culture, etc.?
Yeah, so I'm very lucky that the work that I've done during my PhD has been very synergistic to my contributions at Matmerize. I mean, that's not always the case. But as far as the similarities and differences between academia and industry, I mean, that is a very complex question with different facets, and then the answer to each facet depends on several variables. But with those caveats in place, let me pull on one thread in particular. So, broadly, and maybe this is a little bit obvious, but one important difference is that in research, your primary goal is to solve enough problems to get funding through grant proposals. Whereas at a company or an industry, again, your main goal is to solve problems, but the difference is that your funding comes from the sale of your goods or services. And so this difference can manifest in several different ways. For example, in research, publications are currency, right? That's a saying that we have. Funding agencies want to see you publish with high impact. But depending on the company, they may not see publications as valuable or even as jeopardizing their secret sauce. And in those cases, they may value patents more. So this difference in turn has its own effects. So as a company, if you're protected by a patent, or one of your technologies is protected by a patent, then for some time, it may actually be more beneficial for you to minorly improve your product rather than taking big swings, which have high risk. Whereas in research, minor improvements may be unlikely to get you the grant that you want, which will change your appetite for risk. So those are some things. And of course, there are generalizations. And as you mentioned, the question, or as I mentioned earlier, the question is kind of huge and complicated. So that's the extent that I can go into it, especially as an early career person myself. So I have a lot to learn as well.
Awesome. Well, maybe more about Matmerize. It was founded relatively recently in 2020. Maybe you could talk about, since you've been around in at least his group, probably there's a lot of overlap during that time. Could you specifically talk about what you've contributed and kind of how you've seen it grow in the past 3 years?
Sure. So, yeah, I will talk. I'll go at a high level first and then go down into specific areas. So, at Matmerize, I've mainly been working on technology development or tech dev for short. And broadly, I view our tech dev space as being composed of four different areas. The first two areas are back end and front end. So, in front end, we're concerned with things like, okay, how should a particular web page look to maximize the user experience? In backend, we're concerned with things like, okay, if a user gives us a data set, how do we send that securely in the cloud? Or if multiple users submit jobs at the same time, how do we execute them in parallel in the right way while making sure that our system doesn't get overloaded? Then the other two areas are AI/data science, and then the other one is polymer science. In AI/data science, we're concerned with things like, okay, if a user gives us a particular data set, what's the best way to train a machine learning model? And how should we also analyze the results, like based on the data set? And then in polymer science, I mean, I think that's maybe a little bit straightforward since this is a material science audience, but it's basically translating whatever, knowledge we have from our papers or from textbooks or whatever our classes into something computational. And so that, yeah, that's the high level. And I've had the chance to work and write code that touches each of those four areas. So that's what I did for my first year and a half at Matmerize, was writing the code. And then as the team has grown, I've done less of the code writing and more of the technology development. And so in terms of specific features, I can highlight a few. As I mentioned, you can train custom models on our flagship product, which is Polymerize. There's a lot of knobs that people can turn. Do you want to train a classification or regression model? You can choose. Do you want to train a neural network or a Bayesian model? You can choose that as well. Or you can use the stock models, which I've touched on already. And then there's also a tool that we've recently developed where after a user trains their own custom model, they can see which parameters the model thinks are most important. So let's take lithium ion conductivity as an example. This tool would allow you to see whether changing the molecular weight of the polymer is more or less important than changing the temperature. And so you can actually take this knowledge then into the lab and keep some variables that aren't that important constant while varying the other more important variables. So that's the structure property modeling piece. Then there's also some structure generation algorithms. We have a proprietary algorithm that will generate structures based on a user provided reference structure. So a user will provide a structure that they know how to make in the lab, and then we'll go through and systematically make some variations to it. And we do it this way so that the structures that actually get spit out can be made, right? Because you know how to make the base polymer or base molecule, and then we're only suggesting slight tweaks on that, which also have a high likelihood of being able to be realized synthetically. And then, of course, we have some other features that are less about material science and more about user experience and security, things like single sign-on and encryption and all that fun stuff. So yeah, so that's kind of a few examples of things that we've done.
Yeah. So you mentioned like a whole host of models and different regression and other types of ways to get the final answer almost. My question to you is, number one, for these customers, you can have all these options, but they all have their pros and cons. And so how do you as like the company help them decide what is the best method to do the analysis they're trying to do? And two, as you have more complex models, like you said, one of the key functionalities is letting them know what is most important. And so as you get to like neural networks with more complexity and a black box feature, how are you guys trying to attempt to like still keep a high level of visibility through what your model is doing as you become more complex, which hopefully will give you more interesting and accurate answers?
Yeah, I think the way, as you mentioned, there can be a black box nature to some of these machine learning algorithms. And what we've realized is that the way to remove some of that tint from the black boxes is to tie your models as closely as possible to known chemistry and known physics. So for example, if you want to, let's say you use our stock model to predict the TG of some polymer, you might type in the name of the polymer. We have that functionality. So you might type in polyethylene. But it's difficult for a machine to actually understand what polyethylene means. Like, it's difficult for it to extract meaning from that. So what we do internally is we use our IP to convert that name into some vector of meaningful numbers, like what's the side chain length, or what's the specific substructures that are present in this polymer, what's the minimum distance between rings in this polymer, things like that, things that are like physical observables. And so using that, then when we use our feature importance tool, you can see, which of these chemical attributes are most important for that property. So that gives the user an idea and some confidence that, okay, it's using physical observables to figure out to relate to the target property. It's not using, magic or something like that. So as you tie it to physics and chemistry, which people understand, then people are able to make these results and make these observations and get some interpretability.
That makes sense. So I'm just curious, taking a step back, you've talked about your role in like those four areas from the tech dev side. Where did you learn like the coding aspect? Because your background is in material science and engineering.
Yeah. So it's definitely a bit of a non-traditional route, but I can share my experience about things that helped me. So what worked for me was taking computer science classes. I realized, after my freshman year that I wanted to work at the intersection of computers and material science. At that point, I didn't really know what the options were, but I knew that was exciting to me. So I took computer science classes early on, first as an undergraduate and later as a graduate student. First, I took introductory basic coding courses, learning the basics of Python and Java and R and things like that. And then later on, I took classes with an AI focus. Classes aren't the only way to learn, but the advantage is that you have someone else who knows the field, who's put in time for you in advance and organize the important concepts for you to learn, right? They'll put the easier concepts first and the harder ones later. So they've done that work for you in advance. Whereas if you're self-learning, then that may be a bit of a challenge. You may have to do some of that work yourself. Classes aren't enough though. You do need hands-on experience to reinforce what you've learned and also expose you to new things that you didn't get in class. So I started out doing Kaggle data science competitions. I wrote code for these competitions and I released them open source through GitHub. So that's one key point and suggestion that I have for people is get your code out in the open. And there's several benefits of this. One of them is that other people who may want to hire you will look at your code and will use it to partially assess your merits. So if you have good code out there, then that's a leg up in your favor. Or other people around the world may look at your code and build on it, which is beneficial for you because then you can use whatever tools they've built. Or they may find some bugs in your code and suggest ways for you to improve as a programmer. And for me, I was able to get more hands on experience through undergraduate research positions and also some internships. And so the companies that I worked at and the research positions that I worked at were nice enough to let me choose what I wanted to do. And so I always chose projects with a computational component to them. So that's another key piece of advice I have is wherever you're at, work on, to the extent you can, work on projects that serve you and your interests. And I had all these experiences as an undergraduate, but yet by the time I got to grad school, I was still not a good programmer. So today, 4 years after grad school and 7 years after programming in total, I'm still learning a lot each day. So another piece of advice I'd have is, if you want to get in this field, keep your expectations in check. Don't expect to master this after a few months and work on projects that you enjoy so that you can stay invested for the long haul.
Awesome. Sweet. I really appreciate that advice because I think that'll be especially pertinent for the next generation of MSEs because I think there is a lot of potential in that intersection between computer science, data science, and material science, as you mentioned. But kind of going back to Matmerize, since you've been such a integral part of the company's development, can you share any interesting stories or key learnings that you've uncovered during these past few years of the company's growth?
Yeah, a nice tailwind that I've noticed is general excitement from big companies about AI. They're all looking to integrate AI into their R&D processes. But a challenge is that not everyone is yet clear on how to go about it, and not everyone is ready. There are some people within these companies that are skeptical, and others are scared. And I think a dose of skepticism is definitely healthy. But I think part of it is that there's some misunderstanding. And so, one thing that I want to emphasize is that our products are meant to be digital assistants, augmenting a scientist's work, not replacing it. Right. So, one thing that we've learned is that AI is most effective when there's a partnership between human and machine. And this is something that we know through the research that we've done, having direct experience developing materials. It works best when you're able to kind of marry the AI and the material science. And that's goes back to what I mentioned earlier, is that if you want to make these things interpretable and remove some of the tint from these black boxes, you need to tie it as much as you can to known physics and chemistry. Another misconception is the portrayal in media of machine learning as a sort of like magic or pseudoscience. And of course, this isn't true. At its most fundamental level, machine learning is based on non convex optimization. This is a branch of mathematics that has been around for centuries. It dates back to ancient civilizations. And as a field, it started to take shape in the 17th and 18th centuries with the work of famous mathematicians like Fermat and Lagrange. So those are just a couple interesting things that I've learned and that I wanted to point out through my time at Matmerize.
Awesome. Well, like you said, you've been an integral part of the startup, so we would love to do a case study and dive into a specific application you've worked on for a company. So, without revealing too much, could you share a bit of background about a specific company and then what your technology was able to help them find?
Yeah, absolutely. As you mentioned, there are some confidential details, but I'll share some and keep it high level. I mentioned earlier that we've had a lot of traction around sustainable materials. So that's a space that we're actively engaged in. And one of the companies that we've worked with in this space is Kimberly-Clark, who is looking to develop bio-based polymers for non-woven applications. So they use our platform, Polymerize, to train their own custom machine learning model to predict the mechanical properties of PHA fibers as a function of some chemical variables, but also processing conditions. And so once this model was trained, we used it to virtually screen over 20,000 PHA materials. And of course, this is orders of magnitude larger than what could be done in the lab experimentally in this amount of time. And of those 20,000 materials, we narrowed our focus to 18 of them, which are predicted to exceed Kimberly-Clark's performance target in terms of the mechanical properties that they desire. And so they're currently in the process of making and testing these candidates. So that's one application. Another application in a separate project is a strategic partnership that we formed with Resonac, aimed at revolutionizing the landscape of 6G technology. Predictive models were constructed using Polymerize for key material properties relevant to 6G, including some that I've mentioned already: band gap, dielectric constant, glass transition temperature, but also refractive index and coefficient of thermal expansion. So for each of these properties, we did a head-to-head comparison of our models trained on our platform with third-party models, and we found that in general, our models were consistently more accurate. So once we established this in place, that our models were more accurate, that gave Resonac some confidence, and now they're actively going through and trying to design new materials using these models.
Yeah, so one question I have is that when we think about a material system, it's so complex, and these behaviors and properties that you talk about are inherently linked, right? As everything is. And so when you do these predictive modeling, how much can you simplify versus how much do you have to do like a two-factor, three-factor, four-factor interaction between all these different variables as like inherently, because it is one material, they're all linked. How do you guys handle some of this complexity to try to reduce it to make it simpler to calculate?
Yeah, so these properties, a lot of them are all interrelated. For example, you can typically increase the band gap, but then you'll decrease the dielectric constant. So there's a sweet spot in there that you need to find. And if you only train a machine learning model on one particular property, then it may not learn these trade-offs. So one thing that we've really advanced is multi-target co-learning. Here, rather than training a model to predict just one property, we use a model to predict several properties at one time. So we don't train it on just one property, we train it on multiple properties, and then it can learn the inherent correlations that exist between these. And so that's a good way of kind of preventing your model from overfitting as well. So yeah, I mean that's just kind of one way. Again, mirroring what we know from physics and chemistry is we can use our knowledge of what properties are related together and actually combine these data sets when we do multi-target co-learning.
I was curious about the confidence level that you have in these models, if that is a separate thing that is calculated and how you go about that. Like, when you bring it to a customer and say, we have, 95% confidence that, you should look at these 18 out of X. So I was just curious about that from the confidence standpoint.
Right. Yeah. So not only our models don't only give you a predicted value, like a single point, but we also give you like an uncertainty. So you can kind of use that as like a 68% confidence interval. So we may say the TG is predicted to be 220 degrees Celsius plus or minus 30 or something like that. And yeah, these are calculated based on proprietary algorithms that we have. But I mean, at a high level, you can think about it like, we may train an ensemble of models at the same time. And then we can know based on each individual model in the ensemble what the standard deviation and predictions out of all of them are. And so that's just one way, but then there's other ways that we can estimate the uncertainty as well. And I think that's a really important feature because we don't want to give across the impression that these models are 100% correct because they're not, right? These are estimates. And so uncertainty is one way for you to decide for yourself how much confidence you want to place in each individual prediction.
So when we talk about modeling, usually like the model itself is deterministic, where you input a value, you get one value out. So how do you account for the uncertainty? Is it just like knowing from past experience the range, or by varying what you said? You take like polyethylene, and then you slightly diverge it, where maybe the ring spacing is slightly different, or the band gap is slightly different. How do you account for uncertainty in these models?
Yeah, I mean, the models are deterministic. I mean, there are ways to make them stochastic, but I think just from a practical viewpoint, you don't want a user to like put in polyethylene and then get one value one time and then go back and get
Yeah.
another value the
Mm.
second time. Even though if you do it in the lab, actually you will get slightly different results each time. So yeah, so that's one component of it is there's noise, not only there's noise in the measurements themselves, and then there's also uncertainty in the model just not knowing exactly what the answer is based on what it's been trained on. So I mean, yeah, like I said, there's different techniques that we use to estimate uncertainty, and one of them is like the ensembling approach. But going into it in details, I mean, it gets a little bit mathy, a little bit complicated.
Okay.
Cool. So you've mentioned the Polymerize tool a couple times, and it seems like it was applicable with your work with Kimberly Clark and Resonac. So I just wanted to dive into that a little bit more. Seems like it would be a very useful tool for anyone that works with polymers. So maybe there's like a little bit of an intimidation factor there where people are maybe unfamiliar with AI and maybe won't use it because of a perceived or a real knowledge gap. So I just wanted to get your thoughts on that and maybe a recommendation for students, early career professionals who are trying to get into the space or maybe want to apply it to their own work and how they can go about that if there is a real or perceived knowledge gap.
Yeah, what you mentioned is true. I think there is an intimidation factor. And when we're working with clients, we do some things to mitigate that, like sharing our different publications. And of course, individuals are also welcome to check out some of those publications. So you just search, the Ramprasad group and you get a bunch of different publications. And so that's one thing we do. But then there's also things we do like on the tool itself, on Polymerize. So, and the intimidation factor goes beyond AI and to software in general. And so our recognition of this factor, this intimidation factor, actually predates Matmerize. And so this is why in 2016, Rampi and his group launched an academic tool called polymergenome.org. This tool is a web application which allows thousands of users a year, including, organic chemists, for example, who may not have any coding experience to design polymers virtually using AI. So we take whatever models we build on the research side and we can deploy them to polymergenome.org for people to use. And so this has actually been a big success, in terms of the number of users that we get. And we've taken this lesson to the Matmerize side and made Polymerize a web application. So it's a true no-code solution. But on the Matmerize side, we do work with clients that are programming savvy. And for them, we have an API that they can use to plug into their own existing code bases. Besides the web interface, we also pay a lot of attention to visualizations. I think this is important for reducing the intimidation factor as well, right? We don't want to throw raw data at users. That's overwhelming. We realize that decisions are easier to make when data is organized, and we've built features around this concept. For example, after you train a model, we'll give you a parity plot showing how the model's predictions compare with the ground truth. So on the y-axis, you would have the model's predictions, and on the x-axis, you would have the ground truth. And so not only do we plot the model's prediction, as I mentioned, but we also plot the model's uncertainty. That way you can decide how much faith should be placed in the prediction. And these plots are important, because you can just give someone a metric like, okay, the accuracy of this model has an R squared of this or has a root mean squared error of this. But having the plot there actually, I think, allows people to make the best decisions in terms of, is this model sufficient? Does it have sufficient accuracy, or do we want to get more data, or do we want to turn more knobs on the platform to increase the accuracy of the model?
How much interaction, if any, did you get to have with the customers themselves? Because you were talking about just like there's one component of, gathering the data, but then there's another component of actually communicating it in a way that is easy to understand and drives action. So, did you get any opportunities to interact with customers, and what was that like to be able to communicate a very technical subject and do it in an effective manner?
Yeah, so it really depends on the readiness of the client. And so we have initial meetings, where we give a background of Matmerize and Polymerize, and then, they'll give us an idea of the problems that they're trying to solve. And so based on that discussion, okay, what type of data do you have? What have you tried so far? What internal efforts do you have on AI? We can kind of gauge what their readiness level is. And if they're kind of new to the space, then we can do a shorter term arrangement first where we're more hands on with them and kind of give them a little bit of consulting as well, and then get them to the point where they're ready to then become subscribers. Or we also have clients that are well versed in this space. They know what they're doing from day one. And so they can just jump right on the platform. But that's why those initial critical meetings are important. There's no users that get access to the platform without us talking to them in advance. There's always meetings because the spaces that we're involved in are so vast that it's important for us to understand what they're doing to help kind of give them an initial push in the right direction.
So one limitation that I'm sure that you guys think about a lot is the amount of input data that you can give being from the lab or other scenarios. I imagine that the quality of the data is extremely important, as bad quality data is going to give you a bad model. For this, I feel like as you scale and try to reach other parts, you have to be able to get more raw data in high fidelity. For this problem, is this something that you lead, or are you partnering with others to figure out how to get good data? Or how exactly is Matmerize handling this problem of the incoming quality of data?
Yeah, so I mean, when training custom models, for example, users must rely on the data that they have internally. But data is just one of many requirements. Polymerize takes care of the other important features like data cleaning, curation and analysis, development of model architectures, and training algorithms. In addition, as I mentioned, our chief IP is around chemical representation of polymers. So taking the raw text, polyethylene, and then converting that to something that the machine can understand and do something with. On the data side, though, we also can help when users interact with our stock models. They benefit from the hundreds of thousands of data points that we've collected over the years and used to train those models. And we're continuously collecting and generating more data to improve those stock models. And we also have a feature where users can combine their own data with our data to train superior custom models. So then those models tend to outperform the models trained either on their data or on our data, right? They can actually benefit from what we've done and combine to create a superior model for them. So that's kind of what we're engaged in on the data side. But as I mentioned, data is just one aspect. There's a lot of other aspects that get automated through the use of Polymer.
Cool. So, in terms of the challenges that Matmerize is facing, then are they more like program specific or AI based challenges, or is it people driven in terms of the growth of the company and the next stages of development?
I mean, in science, there is never a last word, but I think we're already at a point where these tools are useful for creating new materials, right? For example, in my PhD work, I used AI to discover a polymer that has 11 times the energy density of the best commercial alternative at 200 degrees Celsius. So that's one example. Other people are doing great stuff in the field of materials informatics, creating real materials using AI. But in the future, yeah, a lot of work can be done to improve these tools. To improve our models, we can either give them more data or we can make them less dependent on data. So to get more data, we're using large language models, think ChatGPT, to automatically extract existing data from text. And we're also working on generating new data ourselves. So that's one piece. Then the other piece to make models less data dependent is a theme that I mentioned before is we're continuing to embed more and more known physics and chemistry into our models. So yeah, I mean, we're already in a good spot. We're in an era where AI can be used to discover new materials, and it's my expectation that these tools will grow in popularity, usefulness, and sophistication in the coming years and help us tackle pressing societal issues like polymer sustainability, for one.
So then I guess you just touched on it, but I would love our next steps like 5, 10 years from now for Matmerize or even this whole space in terms of that intersection between data science, coding and material science. So what are like since you've already been part of essentially a product development cycle and launched a product altogether, what do you think that like the next generation of MSEs could be working on in the development in this area of AI for polymer materials discovery or materials discovery in general?
Yeah, I think, one space which I think David asked a question about earlier is like inverse design. So right now, the our paradigm is okay, we'll start by creating a number of virtual cases and then we'll basically screen them. So we'll select a few and then we'll see which ones actually meet our desired properties of interest. But what if we kind of reverse the direction? What if we start with our properties of interest, put those into a model, and then have the model generate cases predicted to meet those targets? I've done some work on that during my PhD. And so, I mean, there's still some refinement involved that needs to be done before taking that to a commercial level. So that's something that we're focused on over the next couple of years. Another thing is that we've already done this to some extent, but we need to invest more resources into expanding the types of materials classes that we can handle. We've done a lot of work on homopolymers, and now we've started to do work with copolymers, polymer blends, and polymers with additives as well. But then there's also kind of these other stochastic systems like branched polymers and polymer networks. And kind of representing this stochasticity to a machine learning model is a challenge. And so we're exploring directions in that area. And I think it's important because, in industry, some of the polymers that are used are highly stochastic systems. It's not just a homopolymer with a perfectly repeating repeat unit every single time. So those are a couple areas to watch out for in the next couple of years.
Awesome. Well, it's been such a pleasure having you on the show. I know you've already given us some really great advice about how you got into coding and how that kind of evolved over your cycle as a student and now as a professional. I guess maybe more generally, as an MSc, what other advice would you give for our listeners about anything that you think has been really helpful throughout this entire process?
Yeah, I mean, I think just follow your passions, ask a lot of questions. I mean, for me, that's been really helpful is if there's something that you don't understand, don't just breeze by it, keep asking questions until you get to like a fundamental answer or to something basic. For me, like I can understand simple things, so it's important for me to take a complex concepts and kind of break them down into something simpler. Otherwise, I really don't understand it and I can't use it to do science. So yeah, follow your passions, ask questions, and get a lot of reps. So even with, like I said, with coding, like it's important to write open source code, spend hours writing code, and also sharing it with other people so that because writing code for yourself is one thing, but then writing code that other people can use is a totally different thing. So it's important to kind of have this collaborative, almost like community experience, which is one of the great things about computer science is that you can collaborate with someone like all across the world. You can create this huge important piece of software and never have seen the person before. So yeah, those are my high level pieces of advice.
Awesome. Thank you so much, Rishi, for joining us today. This was a really great discussion, and I'm excited to see the growth of Matmerize and see kind of how the material science space continues to integrate with the world of data science and machine learning and artificial intelligence. So again, very appreciative of you joining the show today.
Thank you. Thank you so much for having me on, and keep up the great work with the podcast.
Thank you. Will do. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.